Hello and good day. Today we're diving into a fascinating topic, nuclear energy. To understand nuclear energy, we need to shrink down to the size of an atom. That's incredibly small. At the center of every atom is a nucleus, and that's where the magic happens. Nuclear energy offers incredible potential for clean energy production. It doesn't produce greenhouse gases like burning fossil fuels, making it a key player in the fight against climate change. Imagine the smallest thing you can think of, like a grain of sand. Now, imagine something even tinier than that. That's the size of an atom. At the center of an atom is the nucleus, which is like our sun. The nucleus, particularly the bonds holding those protons and neutrons together, contains an incredible amount of energy. We use a neutron, like a tiny bullet, to split the nucleus of a heavy atom, like uranium or plutonium. When the nucleus splits, it releases a tremendous amount of energy in the form of heat and radiation. And that tiny bit of missing mass is converted into a huge amount of energy. That's Einstein's famous equation, E equals mc squared at work. When we split an atom, it doesn't just release energy, it also releases more neutrons. These newly freed neutrons can then go on to split other atoms, creating a chain reaction. In a nuclear reactor, we control this chain reaction very carefully. These impressive structures might seem complex, but the basic idea is pretty straightforward. They're like giant tea kettles, using the heat from nuclear fission to create steam, which then powers turbines to generate electricity. Surrounding the fuel rods is water, which acts as both a coolant and a moderator. Let's take a closer look inside the reactor core, the heart of a nuclear power plant. Inside this vessel are thousands of fuel rods, each containing pellets of enriched uranium. Control rods made of materials that absorb neutrons are interspersed among the fuel rods. Just like there are different types of cars, there are also different types of nuclear reactors. One common type is the pressurized water reactor, or PWR. Another type is the boiling water reactor, or BWR. In a nuclear power plant, the first step in generating electricity involves harnessing the heat produced by nuclear fission. This heat is used to convert water into steam, a process that takes place in a large vessel known as the steam generator. The steam produced is under high pressure and at an extremely high temperature, making it ideal for the next step in the electricity generation process, driving the turbines. The generator is where the mechanical energy from the turbine is converted into electrical energy. This transformation occurs through electromagnetic induction, a process discovered by Michael Faraday in the 19th century. The electricity generated in this process is alternating current, or AC, which means that the flow of electric charge periodically reverses direction. After electricity is generated, it needs to be converted to a form that can be efficiently transmitted over long distances. This is where transformers come into play. High voltage electricity is then sent through power lines to homes, businesses, and industries. Let's talk about fuel rods, the heart of a nuclear reactor. Inside this tube are pellets of enriched uranium, stacked one on top of another. These fuel rods are carefully bundled together and placed inside the reactor core, the central part of a nuclear power plant. Section 2. Control rods, keeping the reaction in check. Imagine trying to control a campfire with giant metal chopsticks. That's kind of what control rods do in a nuclear reactor. They're made of materials like boron or cadmium, which are really good at absorbing neutrons. Remember those neutrons we talked about earlier? They're the key to keeping the chain reaction going. By inserting or withdrawing these control rods into the reactor core, operators can control the number of neutrons zipping around, push the rods in further, and they absorb more neutrons, slowing down the chain reaction. Pull them out a bit, and more neutrons are free to split uranium atoms, increasing the reaction rate. It's a delicate balancing act, like adjusting the airflow to a fire. Too much air, and the fire rages out of control. Too little, and it dies out. Control rods allow operators to fine-tune the nuclear reaction, keeping it humming along at a steady and safe rate. These control rods are also an essential safety feature. In the event of an emergency, they can be rapidly inserted into the reactor core, absorbing so many neutrons that the chain reaction stops almost instantly, like hitting a kill switch. Section 3. The reactor core. A symphony of energy. Now, let's zoom out and look at the reactor core as a whole. It's a marvel of engineering, a symphony of energy production happening within a confined space. Imagine a giant steel pressure vessel, like a massive pot, filled with water and crisscrossed by thousands of fuel rods and control rods. At the bottom of the vessel are inlets for cool water to flow in, while outlets at the top allow superheated water or steam to escape. This continuous flow of water serves two crucial purposes. First, it acts as a coolant, absorbing the immense heat generated by nuclear fission, and preventing the reactor core from melting. Second, the water acts as a moderator, slowing down the neutrons to the right speed for efficient fission of uranium-235. Surrounding the reactor vessel is a thick, concrete containment structure, like a fortress designed to withstand even the most extreme events. This containment structure acts as a barrier, preventing the release of radiation in the unlikely event of an accident. Inside this bustling core, countless atoms are splitting every second, releasing a torrent of energy in the form of heat. It's a controlled maelstrom, harnessed by the ingenuity of human engineering to power our homes, businesses, and cities. Section 1. The leftovers. Dealing with nuclear waste. Now let's talk about the elephant in the room when it comes to nuclear energy waste. Just like any power source, nuclear power plants produce waste. But here's the thing, it's not your typical trash. Nuclear waste is radioactive, meaning it emits radiation, which can be harmful if not handled properly. Think of it like the embers left behind after a bonfire. Those embers are still hot and can potentially start a fire if not extinguished properly. Similarly, nuclear waste needs to be carefully managed and stored to prevent any potential harm to people or the environment. The good news is that nuclear waste is a relatively small volume compared to other types of industrial waste. We're talking about a much smaller amount of waste for the same amount of energy produced. However, even a small amount requires careful handling and long-term storage. There are different types of nuclear waste, each with varying levels of radioactivity. Some waste, like contaminated tools and clothing, has low levels of radioactivity and decays relatively quickly. This type of waste can be safely stored for a shorter period until it's no longer radioactive. Section 2. Safeguarding the future. Storage and containment. High-level radioactive waste, on the other hand, requires a more robust approach. This type of waste, which includes spent fuel rods, remains radioactive for a very long time, thousands of years in some cases. So, we need to find safe and secure ways to store it for the long haul. Currently, the most common method for storing high-level nuclear waste is in dry cask storage. These casks are like super strong containers made of steel and concrete, designed to withstand extreme temperatures, pressure, and even earthquakes. They're like Fort Knox for nuclear waste. These casks are typically stored above ground at nuclear power plant sites, but there's ongoing research into even more secure storage options. One promising idea is deep geological repositories, where waste would be buried deep underground in stable geological formations. Think of it like putting something in a safe deposit box, but instead of a bank, it's buried deep within the earth. These repositories would be designed to isolate the waste from the environment for hundreds of thousands of years, ensuring that it poses no threat to future generations. Finding suitable locations for these repositories and gaining public acceptance are ongoing challenges, but scientists and engineers are working hard to find the best solutions. Remember how we talked about different isotopes of uranium? Well, it turns out that some of the waste from nuclear reactors still contains usable uranium and plutonium. Scientists and engineers are developing innovative ways to reprocess this spent fuel, extracting the remaining usable material to create new fuel for reactors. It's like recycling on a nuclear level. This reprocessing can help to reduce the volume of high-level waste that needs to be stored long-term, making nuclear energy even more sustainable. Furthermore, researchers are exploring new types of nuclear reactors, called Generation 4 reactors, designed with enhanced safety features, and even the potential to consume certain types of nuclear waste as fuel. These advanced reactors could revolutionize the way we think about nuclear energy and waste management, paving the way for a cleaner and more sustainable energy future. Managing nuclear waste is a continuous process of innovation and improvement. By investing in research, developing new technologies, and implementing rigorous safety protocols, we can harness the benefits of nuclear energy while minimizing its environmental impact for generations to come. So far, we've journeyed from the tiniest atom to the massive structures of nuclear power plants, uncovering the secrets of this incredible energy source. But it all boils down to those special elements that make it all possible. The real stars of the show, the heavyweights of the periodic table, the elements that pack enough punch to power cities, uranium and plutonium. Uranium, often found slumbering deep underground, is the workhorse of nuclear energy. We mostly use its isotope, uranium-235, the one most easily coaxed into fission, that atom-splitting process that releases all that heat. It's like the reliable engine of a powerful machine, steadily churning out energy. Then there's plutonium, a bit of a celebrity, often misunderstood but undeniably powerful. While not found naturally, it's bred inside certain types of reactors, a byproduct of uranium fission. Plutonium can also fuel reactors, even more energy-dense than its uranium cousin. Think of it as a high-performance engine capable of even greater output. These elements, though potent, are not to be taken lightly. Their radioactive nature demands respect and careful handling, which is why safety is paramount in the nuclear industry. But their ability to provide clean, reliable energy makes them essential players in our quest for a sustainable future. As we look ahead, the future of nuclear energy crackles with both challenges and exciting opportunities. We've learned a lot since the first atoms were split, but there's always room for improvement. One key challenge is waste management. While we've made strides in safe storage, finding permanent solutions like deep geological repositories is crucial. It's like tidying up after a party. We need to take care of the leftovers responsibly. Another hurdle is public perception. Accidents, though rare, have left a mark on the public's mind. Open communication, transparency about risks, and continuous improvement in safety protocols are vital to build trust and ensure the responsible use of this powerful technology. But amidst these challenges lie incredible opportunities. Scientists and engineers are hard at work developing next-generation reactors. These designs boast enhanced safety features, improved efficiency, and even the potential to consume existing nuclear waste as fuel, further minimizing the environmental footprint. Imagine a world where nuclear power plants are even safer, more efficient, and produce even less waste. That's the promise of ongoing research and innovation in the field of nuclear energy. In a world grappling with climate change and the urgent need to transition away from fossil fuels, nuclear energy stands as a powerful tool in our arsenal. It's a low-carbon energy source that can provide baseload power, meaning it generates electricity consistently, unlike some renewable sources that depend on the whims of nature. Think of it like this. Solar and wind power are like the sprinters of the energy world, capable of bursts of speed but needing brakes. Nuclear energy is the marathon runner, steadily providing power day and night, rain or shine. By diversifying our energy mix and including nuclear power, we can create a more resilient and sustainable energy grid. But it's not a matter of choosing one energy source over another. It's about finding the right mix that works for each region, considering factors like energy demands, resource availability, and environmental impact. Nuclear energy, with its ability to provide reliable power, should be considered as a transitional route to energy sustainability. By embracing innovation, addressing challenges head-on, and fostering informed dialogue, we can harness the power of the atom to transition to a brighter future for generations to come.